Yeah. So there is only one ready queue for the entire system. It has two pointers. One is head and tail. Head pointing to the first PCB and tail always points to the next PCB. And obviously the last PCB will be having the null value. And these are the device queues, and you can have multiple device queues within the system. Since here there are two magnetic tape unit 0 and magnetic tape units. If you have two magnetic tape units, there will be two different device queues for that. And disk unit 0 and terminal unit 0, separate. So you'll be having multiple device queues within the system. Now, representation of the process scheduling. So the process enters into the ready queue whenever it is created and ready for execution. It is added to the ready queue from the tail end. So and it is taken from the head end and allocated the CPU. So when it's allocated the CPU, it starts executing. While it is executing, any of these things can happen. So one is IO request. So if the process which is currently executing wants to perform an input-output operation, this comes and attaches to the IO device queue. Similarly, if when the process is executing, if a time slice expires, again it goes and attaches itself to the ready queue. So, and then if the process that is executing forks a new child, creates one more duplicate copy of itself, and again it creates a child process, and the child process attaches to the tail end of the ready queue. So, and if it wants to wait for an interrupt, again it comes out. And in case if the process finishes its execution successfully, it will get out of the CPU. Now, so we have schedulers. A process migrates between the various scheduling queues during its lifetime. So one is, there are two types of scheduler. One is long-term scheduler and short-term scheduler. So long-term scheduler, you can also call it a job scheduler. Now, what is its job? Its job is to select the processes which are residing in the main from the disk to the main memory. So this selects the processes that should be brought into the ready queue or into the main memory for execution from the disk to the main memory. And short-term scheduler is also called as the CPU scheduler because it is responsible for selecting one among the processes which are there inside the ready queue for execution or allocating the CPU for the execution. So this is called long-term scheduler because the frequency of execution is very less, and this is called a short-term scheduler because the frequency of execution is very more, because after every process with finishes execution or the process wants to perform an input-output operation, so it gets attaches itself to the device queues, and again the CPU scheduler will make a decision which process from the ready queue should be scheduled next for execution. So hence it is called, this is called a short-term scheduler, and this is long-term scheduler, because long-term scheduler job is to select a pool of processes from the disk and loading them into the ready queue. So the execution frequency of the long-term scheduler is very less, hence it is called as long-term scheduler, and for the other process, so the short-term scheduler, it is more. So same thing I've written here also. Short-term scheduler executes more frequently, long-term scheduler executes less frequently. So next is degree of multi-programming. So it is the job of the long-term scheduler. So when the long-term scheduler is choosing the processes for that should be scheduled, that should be brought into the ready queue, the long-term scheduler should go for choosing the proper mix of IO and CPU-bound processes. Now, what are IO-bound processes? The processes which spend more time on the IO devices, and the CPU-bound processes are the one which spend more time on the CPU. Now, if the long-term scheduler selects only the CPU-bound processes into the ready queue, then the CPU will be kept busy, and the IO device queues will go idle. And if the long-term scheduler chooses all the processes as IO-bound processes, so then the IO devices will be busy and the CPU will be kept idle. So we got to maintain the proper degree between what the CPU bound and also IO bound processes. So hence it is the responsibility of the long-term scheduler to select the proper mix of both CPU bound as well as IO bound processes when it is bringing the processes from the disk to the ready queue. So next is swapping. So partially executed, say if you don't have sufficient space inside the main memory, then the process which is partially executed can be swapped out back to the secondary storage device, and the process whose execution is immediately required can be swapped in to the ready queue, and it can be allocated the CPU for execution. So context switching is the time required for saving the state of the process onto its PCB and reloading the status of the next process that is going to execute to the CPU is called as context switching, and it takes some finite amount of time. And this is always a overhead time, and the system will not do any useful work during this time. So just saving the status of the current process onto its PCB, reloading the status of the next process into from its PCB to the CPU. So this is considered as the overhead time. So next, process creation. Yeah. Now, how to create a new process? So a process can create one more duplicate copy of itself or any number of duplicate copies of the same thing. So we have system calls to do that. So it can be done via create underscore process or fork system call. There is a system call with the name fork, which is most widely used in the Unix based operating system in order to make a process create one more duplicate copy of itself. So when a new process is created, it should be allocated the resources to execute. Now, how the resource sharing is happening? So because we have now two things, one is the parent process and also the child process. The parent and the child, they can go for sharing the resources. So the parent can allow the child to use a subset of its resources, or the parent can deny the child without giving any resources also. So process creation, parent and child can execute concurrently. Parent waits until the child terminates. So Unix examples, we have the fork system call, which is used to create a new process. So exec system call is used after fork in order to replace the process memory with a new program. Say a new process is created, one more duplicate copy of the existing process is created, and if I want to make that new process to perform the execution of something else, then I got to make use of exec. So this exec system call is used in order to make call the execution of another program from within a program. Now here I have a C program for forking a separate process. Now, so here if you look here, PID is equal to 4, this system call is being called. Now when this system call is called, so there is a new child process created. New child process is created and the fork returns twice. So for the parent process, it will return the PID of the child process, and to the child, it is going to return always 0. So for the parent process, PID of the newly created child process is returned, and for the child process, it returns 0. Now this PID, I can weave in two contexts. When I'm weaving this PID from the parent process context, it is the PID of the child. When I'm weaving this PID from the child process context, the PID value is 0. Now if PID is less than 0, so that means whenever the fork is unsuccessful, it will always return the -1 value. Then I just say fork error. Else if PID is equal to 0. So this condition is true for the child process. Now this statement will be executed only by the child process because the PID value, the value returned by the fork to the child process is 0. But the PID value for the parent will not be 0. PID value for the parent is the PID value of the child that is returned. So that will be always greater than 0. Now if else if PID is equal to 0, we are making the child to call this execlp bin ls. The ls command, I think most of you know. So the long listing command. So this is the path where the long listing command is present, and this is the command itself. And I'm not passing any arguments to execute this. What I'm doing now, the newly created child process, I'm making it to perform the execution of the ls command. I'm not passing any arguments. In case if I need to pass few arguments to ls command, I can pass it here. So this is the list of arguments. So list of arguments which I need to pass. And then else part. Since this condition is false for the child, so parent, PID is equal to 0, it's false for the parent. What will happen? It comes to the else part here. So it comes to the else part, and we have the parent waiting by making a call to wait. So it makes a call to wait, and it is waiting for the child process to finish its execution. So when the parent makes a call to this, it will wait as long as any one of its child process terminates. So the moment the child process finishes executing the ls command, it will come out the parent process will unblock, and then it says the message child is complete. This message is getting printed. Who is printing this? The parent is printing, but this execution of the ls command was made by the child process. So now I have one more example to demonstrate the working of the fork function. So this is, I have written here the program. So I've called a fork here. A return value, I'm not assigning it to any variable. Now when this program is executed, so here when the process that is created to perform the execution of this program makes a call to fork, there is one more child process created. So that child process and the parent process both will be calling this. So two process will be making a call to, or two process will be executing this printf, okay, hello USP, and then we have it's two times it is printed. Why it is two times? One time by the parent and one time by the child. So this, when a process calls this, there is one more duplicate copy of the parent process created, and this statement will be executed by both of them. And you cannot tell the order who executed first. LOUSP, this is also LOUSP. Who executed first, whether the parent or the child, that you cannot tell, because the order depends on the scheduler. If the scheduler is giving the priority for a chance for the parent process to execute, this is from the parent process, and next if it is giving the chance for the child process, this is from the child process. So the order we cannot say. So if you want to make the child process to execute first and later the parent process, then you have to use another system called as v4 virtual fork. So that if you're creating the child process or the duplicate copy of the parent process using the v4 system call, so that will always give the priority to the child to execute first compared to what the parent. Yeah, and I have a question here. Some of the students logged out by mistake, and they want to join. Would it be possible to unlock the meeting for a while? I don't know what to do because I'm scared. There's people from outside, they will come in and they'll disturb. I don't know what to do. Sir, Shankar sir? Hello? One second, please wait. So next, I have, hello? Sir, ಅದೇ ಕೆಲವು ಪಾರ್ಟಿಸಿಪೆಂಟ್ಸು ಅದೇ ಡಿಸ್ಕನೆಕ್ಟ್ ಆಗಿ ಹೊರಟೋಗಿದ್ದಾರೆ. ದೇ ಆರ್ ಪುಟಿಂಗ್ ಎ ಮೆಸೇಜ್. ವಿ ವಾಂಟ್ ಟು ಕಮ್ ಇನ್ ಸರ್ ಅಂತ. ಏನು ಮಾಡೋದು? ಅನ್ಲಾಕ್ ಮಾಡಲಾ? ಹಲೋ 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 ಸೊ 163 ಅದೇ, ಬಟ್ ಡ್ರಾಪ್ ಬಾಕ್ಸ್ ಅಲ್ಲಿ ಮೆಸೇಜ್ ಬರ್ತಾ ಇದೆ ಫ್ರೆಂಡ್ಸು, ಅಂದ್ರೆ ಡ್ಯೂ ಟು ಲೋ ನೆಟ್ವರ್ಕ್ ಕನೆಕ್ಟಿವಿಟಿ ಕೆಲವು ಡಿಸ್ಕನೆಕ್ಟ್ ಆಗೋಗಿದೆ, ಅಂಡ್ ದೇ ವಾಂಟ್ ಟು ಜಾಯಿನ್ ಇನ್ ಅಗೇನ್. ಜಾಯಿನ್ ಆಗಬೇಕು ಸರ್, ಪ್ಲೀಸ್ ಅನ್ಲಾಕ್ ಅಂತ. ಏನ್ ಮಾಡ್ಕೋಬೋದು? ಹ್ಮ್ 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 ಅದು ಚೆಕ್ ಮಾಡಬೇಕು ಸರ್ ಒಂದ್ಸಲ. ನನಗೆ ಇನ್ನೇನಿಲ್ಲ ಇಫ್ ಅವ್ನು ಯಾರೋ ಬಂದಿದ್ನಲ್ಲಪ್ಪ ರೊನಾಲ್ಡ್ ಅವ್ನು ಮತ್ತೆ ಬಂದ್ರೆ ಹ್ಮ್ ಹ್ಮ್ ಓಕೆ ಹ್ಮ್ 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 ಓಕೆ 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 say I am unlocking the meeting for 2 minutes. Just inform those who have left to join again. Please try to join with the USN and name, please. Yeah, tell me whether there are students to join. Come in. Hello. Yeah, you in. Okay. Yeah, tell them to join now quickly. Have unlocked. Tell them to join. So because after that I'll be locking the meeting again. Please do join with USN and name. So I request all the participants to just scan through the participant name, and if you find anybody suspecting Karana, please do inform me. I think I'll lock the meeting now. Yeah, told your friends to join. Those who had left accidentally, please. Yeah, I'm locking the meeting. Yes, sir, they joined. Okay, thank you. Yeah, please, all of you mute. Okay. Now, the next program. So don't leave the meeting. If you leave again, I have to unlock the meeting. So it's not possible for me to do this again and again. So program 2, I have written printf creating the child, fork, and then printf creating the child. Now this statement, the first statement, printf creating the child, this will be printed only by the parent process, because at this point, before this, there is only one process. This statement is executed only by the parent. Now after executing this, we have the parent making a call to fork. When it makes a call to fork, there is one more child process created. Now we have two processes, okay, parent and child. So this particular statement will be called by both of them. So both of them will execute this, and you have child created, printed twice. So this is only once creating child, and this is printed twice because the parent also printed and child also printed. This is only by the parent. Next, I have one more example, program 3 here. So I made 3 calls to fork. Fork. Now I want you people to tell the output for this program. So just write your answers in the chat box. Yes, mute. Write your answers in the chat box, please. How many times the child created will print? Four times, 6 times, 7, 6, 7. 13, 4, 6, 4, 8. Okay. 8 is correct. Yeah, stop. See, this 8 is the correct answer. So when the process makes a call to this first fork, when I execute this, say for example by writing this command cc43.c, so there will be a process created by the operating system to perform the execution of this program. So that process, let me call it as P1. So I'll take the pointer. So let me call that process as the P1. The P1 is created. Now this P1 will make a call to this fork. When it makes a call to this fork, there is one more child process created, P2. Now the second fork will be called by both P1 also and P2 also. When P2 calls, there is one more process created, P3. So when P2 calls, there is one more process created, that is P4. Let me call it as P4. Now all these 4 processes will again make a call to what? The last fork system call. And what will happen? All these 4 will create 4 more. So 4 plus 4, 8. So this message, it will be printed 8 times, okay, on the screen. So output of this program is 8. Okay. Next, process termination. Now you understood till now how the process is created. Now the process termination. When the process executes successfully, so it is terminated by making a call to exit. So or you can terminate it abnormally by making a call to abort. Terminate by making a call to abort, we say it is abnormal termination. If it makes a call to exit and terminate, then we say it is the normal termination. Now parent may terminate the execution of the child process for following reason. Abnormal termination of the child can be done by the parent for following reasons. So when the child process has exceeded the usage of some allocated resources, then the parent can go for abnormally terminating the child process by making it to call the abort. So and when the task of the child process is no longer required, again you can make the parent process to terminate. So next, cooperating processes. So we have 2 types of, one is independent and cooperating process. When I say independent process, the process will not interact with any other process. That means it cannot affect or be affected by the execution of another process. It is only independent process. It executes on its own and it will not interact with or do communication with any other processes. When I say cooperating processes, so the process can affect or be affected by the other process. That means it communicates with the other processes which are running within the system. And normally we require the cooperating process in order to share the information for computation speed up, all these things. When you write an application, you'll be having a number of processes running, and it's necessary for one process to talk to the another process. This is what is interprocess communication. Now, and this interprocess communication can be achieved through 2 models. One is shared memory and the other one is message passing. So these are the 2 IPC mechanisms available in order to make the processes communicate with each other. One process talk to the other. So the picture A is showing the message passing and B is showing the shared memory communication. So we have the process A, so sending the message to the kernel, and yeah, and the other process which requires the message can get the message from the kernel. There is something called as message queues. Using the message queues, the process which has the message to send can send the message to the message queue. The other process will get the message from the message queues. And the other way of making the processes to communicate through is by creating a common shared memory. So the process which has the data, it will write to the shared memory, and the process where the data is required will perform the read operation and get the data. So that means the processes through the shared memory, they are communicating by making use of the primitives called as read and write. Now, when I say the message queues, the primitives required are send and receive. So one process will be sending the message and other process will be receiving the message. So those are the primitives required for message passing. Now, cooperating processes can be best explained with the producer-consumer problem. So what is a producer process? The process which produces the data, and the consumer process is the one which consumes the data. So in this producer-consumer can be implemented in two ways. One is unbounded buffer and bounded buffer, but practically it is not possible to have an unbounded buffer. Infinite buffer you cannot have. So what we can do is we can go for implementing the producer-consumer problem using the bounded buffer solution. Now this is the example here. So I have the macro defined with the buffer size 10, and then this is a structure which holds the item and item buffer of size, and I have two pointers in and out, initially initialized to 0. So this is a local variable. Item is a local variable. So this is the producer process program. What producer process does, it produces the next produced item and it is placed in the local variable item. Now while one infinite loop we're entering, now we check whether the buffer is full. How do we check? By doing this: in plus 1 modulus buffer size is equal to out. So if both the same, so do nothing. That means the buffer is full. So just wait for the consumer to consume some items from the buffer and make room for the producer to place the next item. So this while this semicolon says, so the producer process will be keep looping here itself as long as the buffer is full. And next, once there is some space inside the buffer, the data which is there inside the next produced local variable will be placed into the buffer, and the in will be incremented by 1, so that in is pointing to the next empty location in the buffer. Next, bounded buffer consumer process. Here the condition what we are checking is in is equal to out. We are checking whether the buffer is empty. So when the buffer is empty, we need to make the consumer process wait until the buffer is filled by the producer process. So as long as the empty, this condition is true, we have the consumer process waiting. So once this condition is false, that means there is some item for the consumer to consume from the buffer. So it will get from the buffer and it will assign it to next consumed, and out is incremented by 1. So next is interprocess communication through message passing. It can be achieved by using the two primitives what I already mentioned: send primitive and receive primitive. Send will send the message to the intended process, and the process which is making a call to receive will receive the message from the intended process. Okay, this is how it is. Send p comma message, where p is the ID of the process to which the message is being sent, and receive q comma message, where here q is the ID of the process from where the message is being received. So here you don't require the buffer. So the communication happens through message passing. So how the communications happens within the internet, it is through message passing. Even the internet, the communication is happening through message passing through the read and send and receive primitives. So again, in send and receive, we have blocking primitives and non-blocking primitives, all these things. So next, indirect communication. So the messages are not. So this is this send and receive what we discussed here. It is direct communication. That means, so this send, when it is called, the message directly goes to the intended process. And when this receive is called, the process will receive the message from the intended process. Now here, indirect communication, instead of directly sending the message to the intended process or receiving the message directly from the intended process, we have something called as mailbox. We don't have the processes directly sending the message to the other process. Instead, the message is sent to the mailbox, and from there it is received. Okay. So this is like this. Send a comma message. Now a is not the process ID here. A is the mailbox. send the message to the mailbox and receive the message from the mailbox. We don't have the processor specifying the IDs of the processes directly. Instead, they're specifying the mailbox from where the message has to be received or sent. Yeah, so this is again related to indirect communication. You can go through that. Yeah, this Mac, I have one example. You can go through this. Yeah, now we'll come to this. So CPU scheduling. So basic concepts. So we'll understand scheduling criteria, scheduling algorithms, multiprocess scheduling, real-time scheduling, algorithm evaluation. So how to schedule the CPU. Now again, this is the example for the CPU IO bound cycles. I told last class, it is the responsibility of last slides. It is the responsibility of the job scheduler to select the proper mix of CPU and IO bound process into the main memory. So this is this is what the CPU bound, because these are all the instructions which require the CPU for execution. When I say wait for IO, it requires the IO bound because it requires the IO device. And again, this is CPU bound, IO bound. So the long-term scheduler should go, or job scheduler should go for selecting the proper mix of CPU bound and IO bound processes. That is 50% CPU bound and 50% IO bound processes. Next, now what CPU scheduler does, it selects the process in main memory that is ready for execution. So there are many processes which are there in the main memory. CPU scheduler job is to choose one among them for assigning the CPU for execution. Now the CPU scheduling decision is made in all these cases. Now when CPU switches from running to waiting state. So when some process moves from running state to waiting state, again you got to make the CPU scheduling decision. So again, when the CPU switches from the running state to ready state, again the CPU scheduling decision has to be made because the next process has to be executed. And switching from waiting to ready, again you got and terminate. So among this, so 1 and 4, they are non-primitive. That means in this case and this case, you cannot forcibly take back the CPU. Okay, so it happens voluntarily. So whereas in second and the third, it is preemptive. So preemptive in the sense you can forcibly take back the CPU and allocate it to the next process. And we have dispatcher module, and the dispatcher, once the CPU scheduler makes a decision, this is the next process that should be allocated the CPU for execution. This dispatcher module will give the control of the CPU to that process. Now scheduling criteria, these are: one is CPU utilization. Now when you're making the scheduling decision, you should always go for maximizing the CPU utilization. That in the sense you should keep the CPU busy always. Now, keeping CPU busy always will enhance the throughput, increase the throughput, and you got to reduce the turnaround time. So turnaround time is the sum of all these times, the time taken by the process, time the process is waiting in the main memory to get allocation of the CPU, time waiting inside the ready queue, the time the process spends on the CPU, the time it's taking in order to perform the input-output operation, all these times, if you sum, you get the turnaround time. The turnaround time you have to reduce. You have to maximize the throughput, maximize the CPU utilization, turnaround time you have to reduce, waiting time you have to reduce, and response time you have to reduce. So this is what is the scheduling criteria. When you're doing the CPU scheduling, you should look into these criteria. Optimization criteria is this. As I already told, you got to maximize the CPU utilization, maximize the throughput, minimize the turnaround time, minimize waiting time, and minimize the response time. Now, scheduling algorithms have two types: non-preemptive scheduling algorithm, preemptive scheduling algorithm. So non-preemptive scheduling algorithm, once the CPU is allocated to the process, it will keep the CPU until it voluntarily releases. That means it is not possible for the operating system to forcibly take back the CPU from the process once it is allocated to it. And similarly, when I say preemptive scheduling algorithm, so once the CPU is allocated to some process, at any point of time, the operating system has the right to forcibly take back the CPU and give it to the other process. So, and non-preemptive, we don't have these problems. So in preemptive, when you're forcibly taking back the CPU from some process and allocating it to the other process, so we have the problems like inconsistent data, and sometimes it may also damage the kernel structure, because you're forcibly taking back the CPU from the process and allocating it to the other process. Now, these are various scheduling algorithms which we'll be discussing now: FCFS, first come, first served scheduling, shortest job first scheduling, priority scheduling, round robin scheduling, and multi-level queue scheduling. Now, all this, first thing is this FCFS, first come, first served preemptive algorithm. It has two things. One is enqueuer and dispatcher. So enqueuer job is to add the process to the tail end of the ready queue. So I told ready queue, inside the ready queue, all the processes which are ready for execution will be waiting, and it has two ends: enqueuer and dispatcher. So enqueuer adds the process which are ready for execution at the tail end of the ready queue, and dispatcher will remove the process from the head end of the ready queue. And the process algorithm properties are these things. So you got to reduce the turnaround time. So turnaround time you got to compute, average turnaround time you have to compute, wait time you have to compute, and average wait time you have to compute. These are all the things what you got to compute. Now I have the examples now. Example one. So this is the process, and this is the time, execution time. So process P0, it requires 350 milliseconds of execution. Process P1, 125 seconds of milliseconds of execution. P2 this, P3 this. And how do we schedule this using FCFS? First come, first serve. That's easy. I have the PDF. I've already solved it. I'll show you. Okay. So this is the same. I think all of you can see my PDF. The same problem which I showed you in the PPT. So this is called the Gantt chart. You got to write the Gantt chart. So P0, it's starting its execution at 0th millisecond. Since its execution time is 350 milliseconds, it will go till 350. And then we have the next P1 starting, okay, at 350 millisecond. It's starting its execution at 350th millisecond. And its execution time is 125. First come, first serve. So since arrival time is not given, we consider this order itself. P0 is the first, next P1. So 350th millisecond, we have the process P1 started its execution. So plus 125, so it will go till 475. So we have P1 started its execution at 350 and completed its execution at 475. And P2 is resuming its execution, starting its execution at 475 millisecond, and 475 plus 475, it will go till 950 milliseconds. So 950th millisecond, we have P3 starting its execution, and its execution is time is 250. So 950 plus 250, it will go till 1200. And P4, it's starting its execution at 1000 millisecond, and its execution time is only 75 milliseconds. So the 275. So now you got to find the wait time of each process and the turnaround time of each process, and finally you got to find the average wait time and average turnaround time. Now, how to find the wait time of the process P0? So wait time of a process P0 is 0 milliseconds, because see, P0 started its execution at 0th millisecond. So the wait time is 0. And the wait of P1. So P1, to start its execution, it waited till 350 millisecond. So 350 millisecond. And then P2 started its execution at 475 millisecond. So T wait of P2 is 475. And similarly, T wait of P3 is 950, and T wait of P4 is 1200 milliseconds. Now, when I find the average, so this is what I'm getting. On an average, each process has to wait 595 milliseconds in order to get the allocation of the CPU. Now, our intention is to reduce this wait time, average wait time. And similarly, I got to find the turnaround time also. So turnaround time includes the wait time also. Now, the process P0 started its execution at 0 and completed its execution at 350. That means, so the turnaround time for the process P0 is 350 millisecond. So turnaround time for P1 is 475 millisecond, P2 is 950, P3 is 1200, and for P4 it is 1075. So if you just look into this, the left side will give you the wait time, and the right side will give you the turnaround time for this case for FCFS. So and when I find the average turnaround time, 850 milliseconds I'm getting. So this is for this example. So similarly, I want you people to do with this example too, and write the answers in the chat box. Just solve this example 2 and tell me what is the average turnaround time and wait time for this. So average wait time is 9. Some more, can I have some more answers? Average turnaround time? So average turnaround time 10. Okay. Let me check whether it is correct. So this is FCFS. See, average wait is 17 milliseconds and average turnaround is 27. Yeah, I got finally the correct answer, 17 and 27. Okay. Okay, thank you. Now we'll go to the next one. Next, I have similarly examples given again on FCFS, example 3. This is with the arrival time. So the earlier two examples were without the arrival time, but these two examples are with the arrival time. So one I'll show you. So the same example which I showed you in the PPT. So with the arrival time, I'm writing the Gantt chart first. So at time 0, this is the only process which is there inside the ready queue. Now P0 started its execution, and then its service time is 10 milliseconds. So going till 10. So next at 1 millisecond, we have the process P1 entering into the ready queue. So next one, P1 is starting. So 10, it will start at 10 millisecond, it will go till 16. And next P3, P2 is starting its execution at 16th millisecond, and it will go till 18th because its execution time is only 2 milliseconds. P3 starting its execution at 18th millisecond, and it will go till 22 because its service time is 4. Now, when I'm finding the wait time, so since the arrival time is also given, I have to subtract the arrival time. Now I'm finding the t wait of process P0. So how do I find execution start time minus arrival time I have to do? Now P0 is starting its execution at 0th millisecond, and it is getting into the ready queue at what time? 0th millisecond. So 0 minus 0. So the total wait time for the process P0 is 0 milliseconds. Now wait time for process P1 when I am computing. So P1 has started its execution at 10th millisecond, but got into the ready queue at what time? First millisecond. So 10 minus 1. So the total wait time for the process P1 is 9 milliseconds. And then similarly, t wait of P2. So t wait of P2. So P2 has started its execution at 16th millisecond, but getting into the ready queue at 3rd millisecond, 16 minus 3, that is 13 milliseconds. And similarly for P3, when I'm finding the turnaround time, it is 9 milliseconds. So this again turnaround time I'm computing. When I'm computing the turnaround time, so here when I computed the wait time, I did the execution start time minus arrival time. Similarly, when you're doing the turnaround time, it is execution completion time minus arrival time. You got to see when the process is completing its execution and when it is arriving into the ready queue. Now turnaround time for process P0, if I look, say P0 is completing its execution at 10th millisecond, but it is getting into the ready queue at 0th millisecond. That is 10 minus 0. So turnaround time for the process P0 is 10 millisecond. Turnaround time for P1, if you look here, P1 is completing its execution at 16th millisecond, but it is getting into the ready queue at 1 millisecond. 16 minus 1, that is 15 millisecond. So similarly, when I find the average turnaround time, I'm getting it as 14.25 milliseconds. Now I want you people to solve the next problem here and put the answer in the chat box. So quickly. 7.58 time, okay. TAT turnaround time 3.5. Okay, I got few responses. Let me check. So the second one, which I have solved. Oh, sorry. Okay, example 4, I have not solved. Okay. Let me check. Yeah, it's not there. I have not solved. So try to solve it. I don't know whether the answers what you people are writing is correct or not. So just do it because you know the process now. Next. I have one more example. You can copy this and you can try later. Okay, let me go to the next one now. SJF or SJN algorithm. Okay. So when you're using this SJF or SJN, you should know the service time of all the processes in advance. So that is one thing. And the process with the minimum service time always gets the highest priority. And so this will always minimize what the average waiting time and turnaround time. So the problem with this SJF algorithm is that shortage of first or shortage of next is that very difficult to predict the service time because you should know prior what are the service times of each processes, and that is very difficult. And the another disadvantage of the problem with the SJF or SJN is that the process with the longer long service time will have to wait for a longer period of time. That means they'll starve for the longer period of time. That means only the process with the lesser service time will get the priority always, and they get executed first, and the largest process has to wait for a longer period of time. Now I have example here. One is this non-preemptive. First, I'm doing it for non-preemptive. When I say non-preemptive, once the CPU is allocated to the process, it cannot be forcibly taken back until it voluntarily releases. Now, this without the arrival time, I've taken this example, the first example. So I'll go to this. Yeah, this is the example. SJF non-preemptive. Now P0. Yeah, among this, since arrival time is not given, so I'll directly go for choosing the shortest job. So shortest job now is P4 75. So scheduled for execution first 0th till 75. So next shortest is P1. So P1 starting at 75 plus 125 gives you 200. Next P3 plus 250 gives you 450. Next shortest is 350 plus 350. Adding 350, this 450 gives you 800. And to this 800, you're adding 475. It will give you 275. So next, the same problem what we solved for FCFS. So this final time you get the same, but turnaround time and average turnaround time and average waiting time you can reduce. Now, if I find the waiting time for process P1, it is 75 milliseconds. See, so P1 is waited for 75 milliseconds to get the allocation of CPU. And similarly, wait time for process P0 is 450 milliseconds. You can observe here. P0 is 450 milliseconds. And for P2, it is 800. P3, it is 200. And P4, it is 0. P4 didn't wait for any time. As soon as it got into the ready queue, it started its execution. So average wait time, I got it as 305 milliseconds, which is very less compared to what the FCFS. We solved it using FCFS scheduling algorithm also. There it was high compared to this. Now turnaround time computed for all the processes again. So you got to take the right end, that's all. P0 it is 800. P0 it's completing at 800 millisecond, and P1 is completing at 200 millisecond. Okay, so average turnaround time I got it as 650 millisecond. Next. So the other example what I've taken is with the arrival time given. Okay, and again we are solving it using the non-preemptive technique. I go to this. So non-preemptive again, these are the arrival time. So just observe here. So at this time instance, 0.0, this is the only process which is there inside the ready queue. I've written a small ready queue here. So this is the P1. Process P1 is the only process which is there inside the ready queue. Obviously, irrespective of its service time, it will start its execution. At 0th millisecond, we have P1 started its execution. Now let me allow it to execute for 1 millisecond. So till 1 millisecond, I've executed. Now at 1 millisecond, I check again, is there any process entering into the ready queue? At 1 millisecond, we don't have any process entering into the ready queue. Now again, even at 1 millisecond also, this is the only process which is there. And again, we continue it for executing for 1 more millisecond. So it has executed for 2 milliseconds now, 2 milliseconds. And at 2 milliseconds, we have another process P2 entering into the ready queue. So P2 has also entered and its service time is 4. Now, this by the time the P2 gets into the ready queue, P1 has already finished 2 milliseconds of execution and its remaining service time is what? 5 milliseconds. But what I'm considering is non-preemptive. Since I'm considering it as non-preemptive, so we don't have the CPU preempted from the process P1 because it is allocated and it should voluntarily give back the CPU. It is not possible to forcibly take it back. So we make process P1 itself to continue till its completion. Now, by the time the process P1 completes its execution, we have all other process entered into the ready queue. So P2 has entered, P3 has entered, and P4 has also entered at 5th millisecond. So now, since all of them are already there inside the ready queue, next scheduling, I got to find out which is the shortest one. Now, among these three, P2, P3, P4, P3 is the shortest. So this is scheduled for execution and it will go for 1 millisecond. And the next shortest is, we have a tie between these two now. P2 and P4. There is a tie. Now, what you follow? You follow FCFS when there is a tie. So P2 came first, and the chance was given to the P2, and it will 8 plus 2, sorry, 4, 12 milliseconds, and then we have finally the P4 executing. Now again, we are finding here the wait time. So of the processes, execution start time minus arrival time. The process P0 got into the ready queue at 0th millisecond minus started at 0th millisecond and arrival time is 0. 0 minus 0, it is 0 milliseconds. And again, T wait of P2. P2 started its execution at 8th millisecond and got into the ready queue at 2 milliseconds. So 8 minus 2 is total 6 milliseconds of wait time for the process P2. And similarly, I find for all, and I got the average wait time as 4 milliseconds, and the similarly turnaround time when you're doing, you got to find the execution end time or minus arrival time. So I got 8 milliseconds as the turnaround time for this problem. Okay. Now, similarly, I want you people to do it for the another example. I have one more example here. Only 4 processes are there. So quickly do this, and answers are also given. Okay. Just solve this and tell whether this answer is correct or not. And leave your answers in the chat box. Yeah, is this correct? 13 and 6.5. Oh, sorry. This is see, I've written it as preemptive. Okay, I'll show you this. This is not non-preemptive. This is for the preemptive. Okay, I'll go to the next problem. Yeah, I've solved it for one more non-preemptive. Okay, I'll open one more PDF. Okay, preemptive. Yeah. So this is preemptive. Observe now this carefully. So at time instance 0, this is the only process which is present inside the ready queue. So it will start its execution. P1 has started its execution. So P1 has started its execution at 0th millisecond. We allow it to execute for 1 millisecond. So now out of 8 milliseconds, so P1 has already finished executing 1 millisecond, and the remaining time is 7 millisecond. At 1 millisecond, we have another process P2 entering into the ready queue. So I've written ready queue also here. So P2 is entering, and its service time is only 4 millisecond. Since this is preemptive, what will happen? And this service time of P1, remaining service time of P1 is 7, and the service time of P2 is only 4 millisecond. So this is the highest priority process now. And next, the CPU is preempted from P1 and it is given to P2. Now we have P2 executing. So P2 is executing. So it starts at 1 and we allow it to execute for 2 milliseconds. At 2 milliseconds, we have one more process P3 coming and its service time is 9. And this is already finished for 1 millisecond and the remaining service time is 3. Now again, P2 will continue for 2 more. And now P2 has finished its execution. Now by the time 5th millisecond, we have all the process entered into the ready queue. Next, shortest is P4. So 5 milliseconds with 5 milliseconds. So P4 is executing. Next shortest is P1 because this is 7 and this is 9 because this is already executed for 1 millisecond. Now P1 is scheduled and next finally P3 goes. So now when I'm finding the wait time for the process P0, observe here. So start time is what? So P0 started its execution at 0th millisecond, 0 minus its arrival time plus. So started at 0, suspended at 1 millisecond, remained in the suspended state till 10th millisecond and resuming its execution again at what 10th millisecond. So that means there is a wait time for the process P1 from 1 millisecond to 10th millisecond, or you can say 10 minus 1. So 10 minus 1. Execution resume time minus suspend time. So resumed at 10, got suspended at 1. So 10 minus 1 is 9 millisecond. And similarly for P2, so P2 started here at 1 millisecond, got into the ready queue at 1 millisecond, 1 minus 1, 0. That means, so total wait time for the process P2 is 0. That means as soon as it got into the ready queue, it was allocated the CPU and it started execution. So P3, this, and again P2 started here and without any discontinuity, it completed in a stretch. So 5th millisecond, it is finishing its execution. So 6.5 is the average wait time, and similarly turnaround time is easy again. When you're finding the turnaround time for the preemptive algorithm, you got to start. See, I'm finding the turnaround time for the process P1. Start scanning this Gantt charts from right to left. So P1, I'll just start scanning this from right to left for P1. P1 is here. So this time I'll take. This is the turnaround time. So P1 is here also. I should not take this. I have to take this. The completion time 17 minus 0, 17 milliseconds. Okay. Now, if similarly I do. Now, average turnaround time, what I got is 13 milliseconds. Okay. Yeah. So similarly, I have another example here. This example, only the number differences are there. Arrival time is same. Now for this, you have to get, I don't know whether solved it correctly or not. You got to verify 9.75 millisecond and 4.25 milliseconds. Okay. And this answer, I got some answer 11 and 7.75. So maybe you have solved it using non-preemptive, I think. Next, you understood now the preemptive SJF. Next is priority scheduling algorithm. So participant list has come down to 85. So it was at 200 initially. Now it is 85. Only 85 participants are there. Okay. So priority scheduling algorithm. Again, this can be either preemptive or non-preemptive. Here, we assign the priority number to each process. So lower the number, we consider it as the highest priority. Higher number is the lowest priority. Problem with preemptive priority scheduling is, again, the process which has the lowest priority will be blocked indefinitely, and it will starve for a longer period of time to get the CPU allocated. And a simple solution to this problem is aging. That means gradually you go for increasing the priority. So increasing the priority in the sense decreasing the priority number, because the lower the number, higher the priority. So gradually you go for increasing the priority of the process, which has a long, which is waiting for from the long period of time. So by employing this technique or solution aging, even you can give a fair chance for the process with the lowest priority also to get executed. Now again, first I'm solving with a non-preemptive priority scheduling algorithm here. These are the processes, and this is the priority, and this is the service time in milliseconds. Now, lower the number, highest priority. So from this, arrival time is not given again. So arrival time is not there. So this P2 has the lowest number. That means this is the highest priority process. So first this will be scheduled, and next P5 will be scheduled. Next P1 will be scheduled, P3, and then P4. And similarly, you can find the turnaround time and wait time. Now, this problem is with the arrival time. So at time instance 0, this time, so this is the only process which is present inside the ready queue, irrespective of its priority. So you can allocate the CPU to the process P1 and it starts executing. Since I'm saying it is non-preemptive, one CPU is allocated to this. So this service time is 10 milliseconds, and the last arrival time of the process is 4. That means by the time this finishes 4 milliseconds of execution, we have all the process entered into the ready queue, and the priority of the other process are still lesser than compared to the priority of this process. Correct? But still, the CPU can't be preempted from this, because just I'm saying non-preemptive. Okay, I have the problem. I'll just go there. Non-preemptive priority. So same thing. I'll go to this. Yeah, with the arrival time. Okay. So time instance 0, this was the only process which was present, started its execution at 0.8 millisecond, executed for 10 milliseconds. And after that, so now time is 10 millisecond. So you have all the process entered into the ready queue. Now you take the priority. Now which one has the highest priority? P2. P2 executes first. And next in the race is P5. And next in the race is P3. And next in the race is P4. And this you can find out. Since arrival time is given, when you're finding the wait time, do execution start time minus arrival time. Similarly, when you're finding the turnaround time, execution end time minus arrival time. Yeah. So next is preemptive priority scheduling algorithm. So this is preemptive. That means, see, at time instance 0, this is the only process. It can start its execution, and you cannot allow it to continue till the end. So you allow it to execute for 1 millisecond. Say at 1 millisecond, we have P2 also entering into the ready queue, and its priority is lower than compared to value. Priority value is lower than compared to this. Lower the number, higher the priority. Now P2 wins the race, and CPU will be preempted from P1, and it will be given to P2. After P1 finishes 1 milliseconds of execution, so CPU is preempted from it, and it is given to P2. Yeah, 1 second. Hello, sir. Just in an end 2 minutes. Yeah. Yeah. At time 1 milliseconds, so P2 is entering, and its priority is higher than compared to the priority to the P1. So you preempt the CPU from P1 and give it to the P2. So P2 executes, and then for 1 millisecond. At 2nd millisecond, we have this also, P3 coming, and its priority is 4. Now, compared to the priority of P1, okay, so priority of P3 is higher, lower, and priority P1 wins again, and it will resume its execution like this. I'll just show you with the PDF solved one. Yeah, this one. This is preemptive. Yeah. So P1 started its execution. Let me reduce zoom. Yeah. P1 started its execution at 0, executed for 1 millisecond, and then preempted and given to P2. Given to P2. Next, P1 is resuming its execution at 2nd millisecond, and it goes for 2 milliseconds. So till 4. At 4th millisecond, we have P5 coming, and its priority is 2, and that wins the race and take over the CPU. So when I'm finding the turnaround time, so wait time, you got to be careful. Observe here. So wait time of P1 I'm computing. P1 started its execution at 0, 0 minus 0, start time minus arrival time, plus suspended at 1th millisecond, and again resuming its execution at 2nd millisecond. So there is 1 millisecond of wait time for P1 here. So 2 minus 1, 2 minus 1, and again got suspended at 4th millisecond, resuming its execution again at 9th millisecond. So 9 minus 4. So 9 minus 4, it is 5 milliseconds. The total wait time for the process P1 is 6 milliseconds. So like this, you go to find. And turnaround time is simple. So you start scanning this Gantt chart from right to left. When I'm finding the turnaround time for the process P1, it is 16 minus its arrival time. For P1, yeah, I have made a mistake here. So turnaround time of P1, 4 minus 0 I have written. Wrong, this is. Turnaround time of P1 is 16 minus 0. It should be 16 minus 0. I've gone wrong here. Okay. I have completed till the preemptive priority scheduling algorithm. So after this, we have round robin scheduling algorithm, multi-level queue scheduling algorithms. Those things will continue in the second OS training session. Now we'll end the meeting. If you have any queries, you can ask me. And some of you are asking for sharing the PPT after the session. Definitely, I'll share you. Anything else, if you have, you can ask me. And next time when you're joining the other session, tomorrow also you'll be having the session. When you're joining, please do join with your USN and name. So from tomorrow, those will be joining only with the name or some other name which is not readable. So they'll not be allowed. So they will be expelled. So please do join with your USN and name. Both should be there. And in case if you suspect any students who is joining from outside the college, please do inform us. Please do inform us. And if you, recordings of the video also I'll share. PPT also I'll share. And if you have any doubts or the clarification, you can ask me. And the second session, it will be very interesting. It will be on the process synchronization. Many process synchronization algorithms you'll understand along with the round robin scheduling and multi-level queue scheduling algorithms. Also share the solved PDF, sir. Okay, I'll share that. Share. And one more thing, if you're interested, please do join. See, many joined initially, so 220 students were there around, and gradually people are quitting from the meeting. So if you're not interested, please do not join. So let only the interested people join and get benefited out of these sessions. Once again, if you don't have anything to ask me, I thank you all for attending the session and for the patience listening. We will end the meeting. Thank you.